Hi, Peter. Hello, everyone. So I'm going to start this third lecture on bifurcations. So again, I'm not exactly sure what you know about bifurcations, but I'll show you what I assume you know. I don't need much, actually. And our guiding examples for analyzing these bifurcations will be an experiment that has been done quite recently by Adi Chakrabarty and Yves Pomeau and Serge Morin. I have the full reference later on. And it's just gel, which is elastic, but it's very soft, so it has a shear modulus of the order of a few tenths of Pascal. And so it's put in a box. The thickness is a few of the order of centimeter, and the box is turned upside down. And depending on the height, modulus, and weight of the sample, there are two cases. So either nothing happens, and then that's what you see from below. The surface is flat, and you see just black. Or if the sample is soft enough, you see this array of patterns which are actually ridges, right? So it's there's an undulation on the surface, and which you see as ridges, and they organize into this type of hexagons. So it's a nice experiment because it's quite simple. There's no big questions about modeling. You can actually model this as even a neo-Hookean material, which usually is not a very good model, is enough to capture the instability. So it's a finite elasticity, if you want. And the nice thing about this instability is that it doesn't fit into the simple categories which you might have seen already of symmetric pitchfork bifurcation, where typically the instability would be a sinusoid that would appear with a small amplitude. Here you get directly to these crazy hexagonal patterns. So I'll show you that. So we'll start with simple bifurcations where we have the signs, and we'll talk about what you probably know already first. But I'll show you here that by extending the IDs which you already know and pushing an expansion which you have already started by when you do linear bifurcation, then you can capture these types of things. So that would be our ultimate goal for today. Okay? So essentially, the bifurcation analysis is concerned about finding bifurcation that is branch crossing when you're in this phase diagram. So typically we have a system that has load parameter lambda, and x would be the state of the system. And so today we'll be assuming that we know one set of solutions. It's called a branch because it appears as a curve in this phase diagram, in this bifurcation diagram. And so what we will be concerned today is about identifying branches that cross this fundamental branch. So we call it fundamental branch. It's just that's the one we know. It doesn't need to be sampled. It doesn't need to be anything. And so yeah. And today is really about finding crossing. And so it's another type of asymptotic method. I'm not sure if you realize that already. Well, so what I'm assuming is that you probably know how to find the branching points here. By a linear bifurcation analysis, but if it's not the case, then that's not too bad. I don't really need it as a prerequisite. So the outline will be, I'll talk a little bit about the implicit function theorem, because all what I'm doing here revolves about the idea here. I start by studying linear bifurcation analysis, which is really about finding this point, and then I move to weakly nonlinear expansions, which is really finding the shape of the curve in the neighborhood of this point. So finding the other branch locally. And I was saying that this is an asymptotic method, so it's another expansion method, and you can push the expansions to a higher order. And the small parameter that we are dealing with today is the distance along this curve. So how much we perturb the known solution. Okay, so and if you think of that, that fits into the general sets of methods that we are reviewing. So today, our small expansion parameter is going to be the amplitude of the perturbation. So I'm sort of expecting that you know linear bifurcation analysis. How do you call it? Linear stability or yeah, linear stability. It's the same. For beams and plates and other simple structures, what you might learn already, assuming you don't know, you haven't covered that before, is extending these ideas to other models. And the example that I was showing needs, it's not a simple structure. You need it's a slab of elastic material. So we will need to start from finite elasticity. You'll see that. It's nice to use variational formulations for these problems, although it's not completely necessary at this stage. And then we move on to nonlinear expansions, so characterizing the amplitude of buckling and the interactions between mode and more nonlinear phenomena. And doing that, we'll be able to come up with a classification of bifurcation and recipes that you can implement on whatever system you want to really follow the branches and decide what their shapes are. And also, but that's a very important issue, but I don't have time to talk about that. As an outcome of these, you can learn a lot about the stability of the branches, because it's not, I mean, one thing is to classify the branches. Another question, important question, is to know which part of the branches are stable and are likely to be seen in experiments. And all these stability issues are really, most often are very easily concluded once you have listed the branch and followed that. Okay, so that's an important point, but I don't have time to say much. Okay, so just a few words on the implicit function theorem, because that's a simple setting where all the questions we're asking today can be asked. So the implicit function theorem is really when we have an implicit function for some unknown x, which would be our configuration as a function of parameter lambda, which would be the load, and assume that we know a particular point lambda x where where the equation is satisfied, we would like to extend that to neighborhoods. So the naive thing is to linearize this equation and see if a small increment delta lambda and delta x are still consistent with the equation in some place nearby. Then you end up with this linearized equation. And if this coefficient here is non-zero, you can expect that you can find dx over d lambda, that would be the slope of the curve here, in terms of the gradients of f. And that's actually the conditions in which the implicit function theorem holds, and actually warrants that you can find this curve at least locally. Now there's an interesting case where when that doesn't work, and typically that happens when you can't divide here. So when this coefficient here cancels, and that's a situation where, well, you can't apply the theorem and you can stop to guess and try to guess what's happening then there are several possibilities. One possibility is that this quantity is actually becoming infinite because this one goes to zero. So that would be the case of a branch that goes up and falls back. So that's called the limit point. And so in mechanics, it means that there's a maximum value of the load where you lose, beyond which you would lose the solutions typically. And another possibility is that it's a bifurcation point. So it could be that there's another branch here crossing and you're sitting at this crossing point, and that's why you can simply find it. So I'd be concerned mostly with this case. And in the case of elasticity, my implicit function f would be the nonlinear equilibrium. Remember the first lectures, f was the residual of forces in a nonlinear truss, which I can calculate as a function of the truss configuration. An equilibrium is when all these residual forces cancel. And actually, in that case, the function f is the first gradient of the elastic end, of the total energy of the system. Okay. So in that case, the condition where I can expect a bifurcation will be the gradient of f with respect to x equals 0. So that's the second derivative of the total energy, and that's some kind of stiffness. Okay. So when I'm expecting to find bifurcation by this argument when the stiffness of the system is cancelled. Okay, so that's a single degree of freedom case, and we will review the case where we have more degrees of freedom. And since we'll be talking about stiffness, we should recall from lecture 1 that in elasticity, the energy that we are interested in has typically an elastic part, where you first define the strains as a function of the configuration. And in terms of the strains, you define the internal elastic energy. Okay? And there's an excellent part that can handle any type of line load. You might remember that if we do the first variation of this to get the residual forces, so actually minus the first variation, there's a function composition, and you would find this guy, which is the internal stress, this guy, which is the gradient of strain. It's geometric. And that's the applied load. And so we can write the equations of equilibrium in that form, which I think you're familiar with. And another derivation takes us to this form. So because we have a product now, when we take one extra derivative, we have one term where you take the gradient of this, and one term where you take the gradient of this, and that's these two terms. There's another term where you take the gradient of this, which is the stiffness coming from the external potential. Okay, so we'll see these terms. We don't need the detailed derivation. We see these terms coming. So remember that there are three contributions to stiffness, one coming from the external potential, one which is called the geometric stiffness and involves the pre-stretch, sorry, so the amount of internal stress that you have in your structures, time, second geometric quantity, which is the second variation of strain. And the other elastic stiffness is essentially the matrix of moduli. Okay, that's the second variation of the elastic energy with respect to the strains. So again, we'll see that appearing. You just need to have in mind the form of these shapes. Okay, so let me dive into part 1 of the lecture, which would be linear stability. And so that's really what you would do for the Euler problem, where you have a base solution. In that case, you could pick the unbuckled solution that has purely axial load. And then identify special values of the load where you have linear modes that will then give rise to the full branches, but we won't be concerned about the branches for the moment. So we call the method what that gives you the critical load and the branches. Okay, so why do we do that? Well, the first line here refers to the important fact that, so we will be dealing about bifurcation. So bifurcation is really finding curves in that bifurcation diagram. There's a very intimate connection between this bifurcation problem and the stability problem. And again, I won't have much time to tell you about that. But typically, when you walk on the branch, stability is going to change when you go across one bifurcation point, right? So typically, just by looking this, you would be able to conclude that stability is different here from here on the main branch. Now, typically, the case where there's no load and everything will be stable would be here on the left. So you can usually expect that this will be stable. So then this would be unstable. And then these two branches are equivalent because I'm thinking of a symmetric solution. So this will be stable. Okay, so by this kind of this hand-waving argument can be more, can be made more accurate and correct. But essentially, you see that just by looking at the topology of the branches, you can guess what the stability is. You can also do something more detailed, and there are actually methods that are in the direct line of what I'm going to talk in the second part of my lecture that allow you to explicitly calculate the stability of the branches and answer. I mean, if you pick any part of the branch, you can say whether or not it's stable. Okay, and another thing that we learn from bifurcation analysis is that there's actually bifurcation analysis is useful is that there's only a small set of branches, and so there's a limited catalog of situations, and once we've covered them, we're ready to cover about anything. Okay, so let me start with the recipe. Sure.
They include subcritical as a part of the process.
Yeah, not on this drawing, but I will come here later. Yeah. Right, so the discussion I had here, and I showed it, was assuming that the branch is curved to the right, which is called the supercritical case. And we'll see later what happens when it's curved the other way around, which is a situation that occurs in some instances. Okay, so let me start with the recipe. So now we have a configuration which is a vector in boldface. You can think of it as a nonlinear truss. So I'll show you how you can extend to continuous systems, but you need to know the energy of the system as a function of the load parameter and the configuration. Now you have, again, today we are going to assume, and I'll show you in some specific cases how that can happen. We need to assume that we know some particular solution extant. So typically that would be a solution that has a high symmetry and is easy to calculate. Or it could be in a numerical context that it's something we have been able to calculate. We have one branch in the bifurcation diagram, and we are using this argument to try to see if we can move on to other curves. Okay, so in any case, analytically or numerically, you have solved this equation. So the gradient of E of the energy has to cancel along this branch for any value of lambda. And again, that's what I call the fundamental branch. Fundamental here just means it's the one I know. Now the recipe is, and we'll explain where all this comes from, the recipe is that you need to take the equilibrium and so that would be the equation of equilibrium, and then you need to perturb the equilibrium. So you perturb the configuration, and you need and you linearize the equation with respect to the perturbations. That gives you the second derivative of the energy, which is now a function. It's at x and it's evaluated for an increment x1. Okay, I'm not sure if I'm using this notation. No, not yet. Okay, so just look at the first gradient of energy and do one extra linearization. Again, I'm not sure how much you're familiar with notations for variations, gradients, etc. So just feel free to ask. It's simple things, but the notations might be a little bit obscure for you. That would be absolutely fine. Okay, so that would be the linearized equilibrium, and then we just need to insert in that equation. So we focus on this stiffness matrix for those special configurations that lie on the branch. And now we are trying to solve these linearized equations, and we are interested in the special values of the load lambda, which we denote by lambda c because they are called critical, such that it's possible to find increments x1 that are not zero, which satisfy the linearized equations. Okay, so in general, it's not possible. So I mean, typically this could be in general definite positive, so that's not possible unless x1 equals 0. But then there are some values of lambda where this is possible. Okay. Does that sound like well-known things, or yeah? No. For who's never who doesn't connect that with anything he's seen before? Okay, so I'm assuming you're not shy at you know. Okay, so then this set of special values lambda are called the critical nodes. The eigenvectors x1 are called the modes. And of particular interest is the smallest value of the load, because that's usually, but again, we'll discuss that in more detail later. Before the first critical value, you usually expect that you have only the fundamental branch, so the solution you know already. And above that value, you might expect to find different solutions which you maybe have not anticipated before, where your structure might behave differently than what you expect. Okay, so that concretely needs two steps that take more or less time depending on the problem you're looking for. So solving the nonlinear equation for your particular branch of solutions, so identifying your particular branch of solutions, and then solving this eigenvalue problem. Okay, and we've said before that the interpretation of this is that the stiffness in the direction x1 becomes 0, so your structure is soft and might want to follow a different set of configuration in this direction pointed to by x1. Okay, so I'm going to start to use these variational notations. And the rule will be that, so this d is a gradient, right? It's what I've noted. This is actually the gradient of the energy with respect to x, or you maybe, I'm not sure which notation you use, maybe you write this or something. So there's a division by dx, right? So the rule of the game I'm going to use now is that I will never divide by dx, and instead of this, I'm going to consider the increment Okay, so I will prefer to use that instead of that. I mean, it has the same content. This is a linear form, so that's something which for any increment dx, which I keep, gives me the corresponding change of energy. Right? So the reason I want to do that is that this has a sense, this has a meaning only in the discrete setting, while this is very easy to generalize when you have continuous structures. And I'll show you examples of continuous structures. Okay, so this is now the variation of E. So it's a linear mapping that depends on where, what configuration I'm linearizing about and what's the value of the node. And it's linear with respect to the increment I've specified. Okay? And same for second derivatives. I show example here. So the second variation, sorry, that's now a bilinear form that depends on two increments. And again, I show you examples, and it's furthermore symmetric. So you can just think of the discrete case as the case where this increment is just the multiplication by the gradient. But again, I prefer this notation because I will deal with some cases where the gradient does not make sense mathematically. So that will continue to make sense. And that is the first variation. Okay.
What is the square bracket? You know?
So my notation for the square bracket is anything I feed to this linear application, and that's just to make it clear that so this expression is going to be linear with respect to anything inside the square bracket, but non-linear with respect to this. Okay, so that's the point where the gradient is evaluated, and that's the linear argument. Okay. Another benefit of this notation is that it's very easy to take into account kinematic boundary conditions, other kinematic constraints, just by restricting the kind of virtual displacement you're using. Okay, and you see that for there's another reason for bifurcation analysis where it's desirable to keep this silent variable or dummy variable, which we call the virtual displacement, because we need it to for the nonlinear variation. So is that maybe okay? So let me just go to cover a few examples, and hopefully that will all become clear. So the simplest example for a bifurcation would be the discrete elastica. So it's a 1 degree of freedom elastica where we have a rigid bar on an elastic hinge. The configuration is given by the angle of deflection theta. The energy would be the hinge energy, that's a function of theta, which we assume to be even. So we, in particular, will have that the moment is 0 in the vertical configuration, because that's supposed to be the natural configuration of the hinge. And then lambda will be some force that's applied actually. So it's exactly the classical elastica, except that the elasticity is now concentrated on a single point. So it's easier to add. So, okay, you know that you could look at maybe you know that you could look at the stability criterion directly by calculating the second derivative, but I want to do that using my own set of notations. So first, let me look at the first variation of that. So I replace theta by theta plus some increment, and I take h goes to 0, and I linearize, and then I see whatever linear term in h I have. So that's really taking a variation of this initial energy. So when I do this, I get that. Okay. And that's, so in that case, I happen to be, it's easy to eliminate theta hat. So I could do that, and then I get the nonlinear equilibrium. Okay. Now this nonlinear equilibrium has an obvious solution, which is the fundamental branch, where theta is always equal to 0. So that's my fundamental branch. And if I apply the linear bifurcation analysis, the recipe I just gave, the problem now is to find a value of lambda such that the linearized equation here, so this is an equation in weak form, theta hat is a virtual displacement, I could get rid of it, it's a dummy variable. Now I linearize once more, so I need to replace theta by yet another quantity, so now I replace it by theta plus h theta 1. So I take one more increment, and now my theta 1 is the perturbation in the real configuration. I do this, and as I said before, so that would be 1, 2, and then at the end I replace theta by theta naught. Okay, so I do two variations and then I evaluate what I get along the fundamental branch. Okay, so that's why I have 0 here, for instance. That comes from this. Okay, so it looks. I know it looks like an overkill for such a simple problem, but you'll see that we can. The benefit of this is that we can always apply this simple recipe. So that's what I get here. Again, we could easily remove the theta hat because it factors out. But the point here is that we have an equation that selects the critical value of lambda, where this second variation has non-trivial solution. Theta 1, that's when lambda L and this W star cancel out, and then you find the root. Okay. Now we can do exactly the same thing for the continuous elastica, and we would start then from this energy that has a bending term. So here I'm using a linear quantitative relation, so that's a linear beam, right? This lambda cosine theta is the position of the projected position of the endpoint here. So, sorry, integral of cosine theta is the position of the projected position of the point here. So the work of the external force is lambda times this. So that's my total energy, and I could be using clamping conditions, for instance, and then I have theta equals 0. So then we do exactly the same recipe as before. We look at the first variation of energy, so we do this, but now theta is a function, and we get the nonlinear equilibrium. Okay, it's in weak form. We have introduced some auxiliary function theta prime, which we can remove, but now to remove it, we need to do integration by parts, right? And if you do that, you know that you get to the equations of the elastica, nonlinear beams, and you also get the missing boundary conditions. So all this work of doing the integration by parts, it's on you guys. Okay, I'm just going to stick to the variational formulations because it's better. I want to stay high level. Okay, so you have this, and the point is that, well, that's reasonably complicated, but in general, this nonlinear equilibrium you can solve in full generality. It happens that for this particular problem you can, but I won't be concerned about that. And we are trying to apply the linear bifurcation method for this equation. Okay, so here we have an obvious fundamental branch, which is the unbuckled configuration where theta is everywhere 0, and that's what we use for our bifurcation analysis. And then we apply the same recipe again. So we take a second variation, right? We start from the nonlinear equilibrium, we take a second variation. So this term here is already linear with respect to theta, so that makes theta 1. And this one is sine, so when you linearize, it becomes cosine theta times theta 1, and cosine theta you need to evaluate on the unbuckled branch, so the cosine theta becomes 1, and you have this second variation. And okay, so now it's a linear problem for theta 1 that has an eigenvalue lambda, right? So usually this problem, again, in this problem you can integrate by parts, turn it into a linear boundary value problem. I leave that to you. It's actually written here, and you'll find the linearized equation for the elastica. Point is that you won't be able to satisfy all these equations except for special values of lambda, and these are the modes of the elastica, which again you probably know already. So this way we are able to select values of lambda, special values of the load, and we also have, by solving these equations, the mode shape that are associated with them. Okay? We can do that for another interesting situation, which is a strut, so beam resting on a linear foundation. So that's a simplified representation of a hard skin on an elastic slab, for instance. It's simplified because we assume that the elastic slab here is just represented by spring, so it's a local interaction, for instance. And then the energy of the system would be like this, right? So there's a bending term, there's a term that captures the stress which is applied here, which tends to make to induce slopes. So that this lambda, when it's compressive, tends to, well, the preferred configurations are those that are tilted. It's a classical effect of pre-stress, and then we have this elasticity term coming from substrate. So we can again apply the same method. We have the one variation gives me the nonlinear equilibrium. I have one analytical solution. I can linearize the equilibrium, so do one more variation, and then I have something that depends on y hat and y1. Y hat is my virtual displacement. I can eliminate. Y hat is my mode. That's the eigenvector. And you know you get a fourth order ODE when you do that. It has constant coefficients. So you can derive from that a dispersion relation where Q would be the wavelength in the x direction. And the interesting thing with this system is that now, if you plot the dispersion relation in the lambda Q plane, you typically get something like that. And you find that the first, so in that case, you really have a continuum of critical loads. But the first one corresponds to a particular value of, well, the first load is given in terms of the system parameters, and there's a special wavelength also which is given. So all this region would be unstable, and when you increase the load, you see that the system first picks a mode that has a specific wavelength. So that's typical of a system which is going to, where the bifurcation is associated with a special wavelength, right? So that's typical of systems where you will see a specific pattern with a specific wavelength appearing when you increase the load. So a slightly more complicated version of that is this problem I mentioned quickly in my first lecture. So that's a thin film that's sitting on top of the hot sphere. So that's the cut view. The film is here, and the two are connected by a capillary bridge, right? So that's using a fluid which is dyed in yellow. And so what the fluid wants is that it wants to increase the surface of contact between the film and the sphere. What the film wants is minimize its elastic energy, and that entails, for instance, trying to remain developable. Okay, so the two constraints are incompatible because, of course, when you stick to the sphere, you can't stay developable, and then there's some energy to pay for that. And so this problem can be analyzed by using a thin shell theory and adding some term that accounts for the capillary interaction. That would be just the capillary tension times the area which is in contact with the sphere. Okay, and then you can, so that's a complex problem. There are some boundary conditions that take into account the capillary bridge. The Shell's equations are not super easy either, but for that problem, you can identify a reasonably simple solution, and that's shown here. It's the case where the cylinder has a shape that's axisymmetric, like in this drawing. So that would be axisymmetric. So then there's a rectangular region of contact here, which is what you see here in yellow. And so to solve, and that's what we will use as the fundamental branch, right? So we have to solve these Shell's equations in axisymmetric geometry. Of course, it's a lot easier because if it's axisymmetric, it essentially only depends in one variable. Everything is invariant along this theta direction. So that can be done, and then you can analytically calculate these configurations. And then we do the trick of looking at the linear bifurcation criterion, and when we do that, this ends up with something pretty similar to that. So the load parameter here would be sigma, and sigma is essentially the capillary force, the surface tension. And there's an extra parameter which is an azimuthal wave number, right, associated with this variable theta. So this k is the periodicity in this direction. So now it's a left-right symmetric problems, and for these types of problems, you need to consider perturbations that are either symmetric or mirror symmetric. Well, either mirror symmetric or skew symmetric with respect to the vertical axis. And for each type of perturbation, you can calculate a curve like we have here, right? And you do this. I mean, these curves really come from the cancellation of the stiffness. That's exactly the same thing we were doing before, except it's with slightly more complicated equations. Okay, and when you do that, you find that in these two curves, the minimal value of sigma, so that's where the load, the first critical load corresponds to these undulating shapes, and you can calculate the corresponding load, and you can calculate the corresponding wavelength, right? So with this linearized theory, you have a prediction of when you expect the pattern to appear, what its wavelength is going to be, and you can also get a hint that another type of pattern is not possible. So it's interesting for this problem because you have a selection of the load, the wavelengths, and the pattern, and it actually works very, very, very nicely. So that's essentially the wavelength. That's essentially the radius of the sphere, so it's equivalent to this parameter. And then there's this prediction for the wavelengths that's compared to the dots in the experiment. So it's a linearized theory that works very, very well. But it's linearizing a nonlinear shell, okay? And all this is done analytically. It's not difficult, and it's a lot easier than setting a finite element of shells. Okay, now, first attempt to tackle the Rayleigh Taylor instability. So let's see if we apply this recipe, what we get, and whether it can be consistent with what we see in the experiment. So I just start by introducing the energy. I make no variation for the moment. So the main the kinematical description will be to find the position lowercase x of the point, capital X. So that would be the mapping, the deformation map. And we have this constraint that one plane here is attached. So the displacement is constrained to be 0 at the bottom of the box. Now we do finite elasticity. So the main the measure of strain will be our Green-Lagrange strain, right? So that's this quantity in terms of the deformation gradient. And then we just do finite elasticity. So we assume that the energy of the system is going to be the integral in the slice of this W of E, which is my whatever constitutive law I want to use, plus the effect of gravity. So what I call lambda here is rho g, right? So the volume density times the acceleration of gravity, and that's my model. Okay, so let's try to apply the recipe for linear bifurcation for that and see what we can try to predict for as patterns. Sure.
What was inside the box?
So the box is filled with a gel.
Gel.
Right? And it's an elastic gel. And then you just turn the box upside down. So in practice, it's just a very soft, well, everything you see is reversible. So if you turn the box upside, back to the upside, you don't see anything. So it's just an elastic slab. Right? Okay, so the linear stability, we are first trying to derive the nonlinear equilibrium from this by introducing a perturbation x. So it would be x hat, and this is one of these components, and see what's the first variation of the energy looks like. And by canceling the first variation, we have the equations of equilibrium, okay? Modulo some integration by parts that I, again, leave up to you. So when I take the variation of this energy, it's like the general formula I was showing before. That's a composed function because E is a function of capital X, right? So I have dW over dE. That's my Euler-Kirchhoff stress. That's the constitutive law. And then I have dE over dx, and that's just geometry. You can show it as this expression. So that's one piece, and the other piece is easy. It's just this, right? Okay, so now this f hat is the gradient of x hat. So there's a gradient. So if you want to get to the equations of equilibrium, you need to do the integration by parts, and you end up with the classical equation, you know, in finite elasticity, that the divergence of some stress plus the external load is zero. We are just a few lines away from there. But I don't want to divert your attention. We'll stick with this variational formulation. Okay, now we have the nonlinear equations of equilibrium. We need to find, hopefully, a simple set of configuration, which we call the fundamental branch. And here, we just use the unbuckled configuration where the slab is just hanging from below with a flat surface, right? So it's easy to convince yourself that, okay, well, by the way, here I haven't specified what I use as a constitutive law, so that in the real work we use an incompressible material, but incompressibility complicates a little bit the formulation because we need to impose extra constraints. So just let's forget about insensibility and let's just take some material coefficients such that the bulk modulus will be much larger than the shear moment. Okay, so everything will be then even in the trouble. Okay, so we have to assume that this is, let's say, mildly incompressible. So when we are flipping upside down and trying to find this base configuration, there will be some stretching, right? So this will slightly move downwards. And the problem now is to find the position Z in the slab as a function of the original position, right? So we are really describing this homogeneous solution. So that corresponds to assuming this form of the deflection. So the final configuration, whoops, sorry, that should be capital X, capital Y. So the X and Y coordinates aren't changed. And we are assuming that the final position is now a function of just the initial vertical position. So the final elevation is a function of just the initial elevation. We can plug this into the nonlinear equations of equilibrium, and of course it becomes much simpler because that's effectively a 1D problem. I have only one unknown, only the Z variable that's there. And actually, this problem becomes very similar to the problem of a hanging extensible string, right? So it's an extensible string that's hanging under its own weight. And you know how to solve that. You take an imaginary cut by writing the balance of the lower part of the string. You can guess what the internal stress is going to be. And if you invert the constitutive law, you find the stretch from this internal stress. So that's exactly what guides the solution. And you end up with an explicit formula for this theta. So that's going to be my reference configuration. And again, my fundamental solution, as you see, is making some assumptions, assuming that the symmetry is preserved here. Is usually reasonably easy to calculate. Okay, then we can do one more variation here. And very much as in the formula for the stiffness that I was showing at the beginning, we have 3 terms. So, well, the simplest one is the one coming from the external potential. This doesn't depend on x. So when you do one more variation, it cancels. So the stiffness from the external potential is just 0. And we have 2 terms coming from here. One term, that's another derivative. So that's dn over dE times the gradient of E. And that's this. That's dn over dE. That's the elastic moduli, elastic stiffness. The gradient of E is this one, and it's the same as the gradient of E we introduced in the first variation. Okay, and now there's another term which comes from varying f here, which depend on x, and I get n, which I now have to evaluate in the base configuration, so that's going to be called the pre-stress, times the variation of this one, but this one is linear with respect to x, that's the gradient of x. Right, so that gives me f1 when I linearize. And well, maybe you recognize this is the second variation of the elastic energy with respect to E. And this is the term that I was writing BTKB when I was dealing with nonlinear trusses. That's the elastic stiffness term. And this term depends on the pre-stress and the second variation of the geometry of the strain, and that's the geometry stiffness. Okay. And so typically that's what you would implement in finite element numerically if you would like to check stability numerically or anything. Anyway, so now this everything that bears a knot refers to that fundamental solution and is known. There's a small glitch here. So everything that bears a knot is known. Everything that bears a hat can be gotten rid of by integration by parts. And if I do the math, I'm left with a problem that's linear with respect to x1, my unknown, so y's. And depends on the value of lambda. So the dependence on lambda is hidden here because that's the, well, especially here, that's the pre-stress which you get from the solution and this guy. And like in the hanging chain, the pre-stress in the chain is going to be a function of how much load you apply. So there's a hidden, well, it's not explicit in my notation, but remember that this one depends on lambda. And again, I need to find solutions to this linear problem, and in particular find the special values of lambda, which make it possible to find solutions in x1. If you think a little bit about this, so this is a hanging block, you realize that there's a direction, that the problem is invariant in all directions in the plane, right? The block looks the same if you turn it about the vertical axis. Okay, so that suggests looking for the modes x1 in this special form. So the mode has to be, and I think it becomes clear when you look at this drawing. So these modes, the way you look for modes will be something that's harmonic in some direction of the horizontal plane. So that's this. And here I'm just assuming that the wave vector is aligned with the x-axis, but actually it can be in any direction of the xy plane. So I'm saying this by mentioning that the orientation of the x-axis is actually arbitrary. So it has to depend harmonically on this in-plane variable. And it may depend, and it has some extra dependence on the z variables. Okay, that we don't know. So we just need to plug this special form into this problem and solve for the tilde quantities. And then we come up with, it's actually doable analytically, and there's a solution that gives you these expressions as well as the value of Q, as well as the value of the load. Okay, so it works exactly like before. the starting equations are a little bit more complex, but the method is exactly the same. And if you do that, you select the value of the load. So that's, you remember that's rho g. The critical value of the load, and you find a universal value. So I mean, so the real bifurcation parameter would be the ratio of rho g to the shear modulus times the thickness. That's just by basic scaling analysis. And you find that this parameter has to have some magical value for the first bifurcation to take place. And you can also, like in the problem I was showing before with the sphere and the film, you can also select the wavelength. So let's see what that gives. So this is lambda, essentially. That's rho g, which is lambda. So that's lambda bar, right? So it's a dimensionless form of lambda. So that's my loading axis. And the stars here are measurements from the experiments. That's the amplitude of buckling measured by the height of the wedges. So this is where we have the prediction from the theory. That was 6.22. And this is what we see in the experiments. What we see in the experiment is that nothing happens. And then there's a discontinuous transition where the amplitude is really non-zero. We see hexagons and not stripes, as we were expecting from the linear analysis. The threshold is not correct. It's significantly below in the experiment. So you see the bifurcated pattern appearing below. So everything is wrong, right? The critical load is wrong. The pattern is not correct. Oh, and there's one thing, I didn't show the data. There's one thing which is correct. You can compare, you have this QC, and you can compare to the periodicity, well, that gives you a spatial wavelength, and you can compare to the width of the hexagons, and that works. So in some sense, it's reassuring. Okay, so the second part of my lecture, and I'll probably be only able to finish next week. The second part of my lecture is explaining how you fix that classical linear stability analysis to explain all that and restore consistency. One hint here is that, remember that the direction here in the plane is unspecified, right? Just because the system is invariant. So we select a wavelength, but you have stripes in all directions. So what's specific with this system is that there's not one buckling mode, but an infinity of buckling modes corresponding to all possible thetas in the plane, right? So the crucial question we need to ask now is it possible for these buckling modes to collaborate, work together, couple, and maybe couple this pattern, and maybe get to this pattern? So what we'll show, and we'll take a small pause, what we'll show is that indeed, when you take coupling between the different modes into account, you exactly get to that picture, right? And that hexagons patterns are just a particular combination of the buckling modes. Okay. So what about a small pause? 5 minutes? I probably need it. Okay.
You would try the answers for the one.
Oh, that's a good question. That's a good question. I should probably answer in front of everyone. So yeah, you would change the answers here. Yeah. So the problem is that if you do that in linear stability analysis, your linear bifurcation problem is linear with respect to the quantities one. So I'm not sure which ansatz you would like to use, but typically you could try a superposition of these things with different wave numbers. And the thing is that everything will decouple. Because that's a linear problem, you can't find if there's any combination of this is going to work fine.
Yes.
So the hexagons won't work fine. So the hexagons are actually combinations of 3 modes, right?
Okay.
So if you insert that in that linear problem, there's no way you can get an information on how the things can couple together. That's because this equation is linear.
Yeah.
But you're right in the sense that what we will do is to try to push the expansion with respect to the perturbation one order further, and then we have a nonlinear equation here.
Okay.
That can tell us how different modes like that can couple together. But so you're pointing exactly in the right direction.
But the couple that can be self-analytic or just numerous?
Mostly analytical, and that's what it's quite surprising because the problem looks difficult, but symmetry is playing a very strong role here, and there's only one constant that needs numerical evaluation if you want, but for the rest it's all analytical. So that's what I want to share here.
I was going to ask. So is it like he's going to come back down and like this pattern?
Yeah, that's tricky. I want to describe it so far. So this one is actually a transcritical bifurcation.
Yeah.
So it's like that.
Yeah.
And it's
Okay.
And you can tell that.
So actually, you were showing the rest is like the answers in how it reaches the exact.
Sorry.
Yes.
Right from here, yeah. Is that what you're saying? So actually, the branch is like that.
Yeah.
And the reason it's like that is because you have you can't you have two different types of hexagons. Some that have hollows and some that have stuff. I'll show that in a minute. So it's not so much. That's the usual reset of it. No, but if somebody is just no, that's fine. Okay. I'll probably skip that. Does it seem like something? Yeah. Yes, I sent it out. I looked at So John is really, I think John, the previous slide. Yeah, good. Okay, probably we can resume, right? Well, time is passing so fast. I have no idea whether it was 2 or 30 minutes. Okay, so the second part of the talk, and I will have to find a place to stop. So we probably won't have time to go all the way through, but it would be nice if I set the stage and give you the general results. So maybe we'll just apply them just next week. So the idea here is really to, now that we know points where something is happening, the idea is really to construct the other branch. And that's called the Lyapunov-Schmidt-Coiter expansion. Here is the image for your Cauchy. Yes. So And as you see, so we'll be able to build the branches in a small neighborhood of the point, and that's already very useful because typically that helps discriminating between these two situations. So that's the case of the symmetric bifurcation, where there's a symmetry argument, just because your system happens to be symmetric, that tells you that whenever you have a bifurcated solution, you have also another bifurcated solution that has exactly the same energy. So typically, if you think of the elastica, you have one buckling on one side or the buckling on the other side, and they should be equivalent. So you need to have this parabolic shape. But you can't tell, unless you do detailed analysis, whether the parabola is on the curvature to the right or to the left. And usually there's this argument that tells you that if it's to the right, then this part is stable, and if it's to the left, this part is unstable. My point is that just by looking at the sign of the curvature here, you can discriminate between these two things. And the sign of the curvature, that's the parameter lambda2 that I'll show you how to calculate right now. Now that's the non-symmetric situation, and in the non-symmetric situation, the general argument is that you should always have one. For any value of lambda, you should always have one value of the one branch which is stable. So if it's tilting like that, stability goes from this one to this one. If it's tilted the other way, it will go from this one to the other side. Okay, so again, it's just a generic argument, and again, there exists some well-justified version of that. But my point is that just by looking at the sign of the curvature or the sign of the slopes, you already have a hint on what's the curvature, what the stability should be. So another case where we need these linear expansions, it's that these linear expansions explain how the buckling modes couple, and that refers to the slide I was showing on the elastic Rayleigh Taylor instability. We have many modes, and we don't know how they need to be coupled. That can be done in the framework of this method. And a very important application also, which I won't have time to cover, is the case of imperfections. I'll come back to this a little bit at the end, but that historically, that has been a huge success, mostly due to Coiter, to use this framework here and use it to explain the very strong importance of imperfections, at least in some specific cases that were important in practice. Okay, just a small word. Oh, now the time is stuck to noon. Just a small word before we start. And that's not very well known. So you can even find papers that get it wrong. Well, often the structural models that you would tend to use for studying buckling problems, typically the elastica, nonlinear beam. Often these models have assumptions that are hidden in them, that are really tailored for linear stability analysis. So the elastica is perfect for studying the buckling load, but they are not applicable beyond that framework. And I'll give you a very specific examples where you end up with wrong predictions if you use the linear elastica. So I'm just saying, yeah, I'll give you examples later on. I'm just saying, be very careful when you start to do these nonlinear expansions or nonlinear calculations. Be careful whether the model you want to use makes sense in this context, and it's not always the case. So a typical case is the von Karman plate model, which everyone knows is weakly nonlinear. It works very well for linear bifurcation analysis. It predicts buckling load, but if you try to use it just the next step beyond that, it gives wrong answers. So let me explain what's happening here. So essentially, I'm not sure if you have the von Karman plate model in mind, but essentially it uses a stretching strain which is linear with respect to the in-plane displacement. So you can view it as a linearized version of the true nonlinear geometric strain. So that's what I call the non-linearized version. And then it's quadratic with respect to the transverse strain. So that could be seen like the second expansion of this fully nonlinear strain. So these expressions that you use for the Von-Karman model is essentially the Taylor expansion to order 2 of a geometrically nonlinear strain. It's in any case it's quadratic, while the true nonlinear strain is fully nonlinear. Okay, there's also an approximate measure of bending strain. I'm not going to speak about that, but it's essentially the same problem here. And also, typically, a Von-Karman plate would use not linearly elastic constitutive assumptions. So that would be a constant. That would be your constant elasticity coefficients, and your energy is quadratic. So that's okay. All these assumptions are okay for bifurcation analysis, and you can actually see that. So this would be the linear bifurcation problem for the plate. We always have this term, so maybe you recognize here. That would be the pre-stress. That's the first variation of the strain. So that's the geometric stiffness. That's the matrix of moduli. So that's the elastic stiffness. So that typically would be the terms that you have in your plate buckling problem. And you see that this involves these 2 variations of the energy. So that's the tangent moduli. This involves second variation of the strain. And these quantities are exactly those that are correct in this model, right? Correct meaning that they match the ones you would get from the true nonlinear theory for large rotations. Okay, so what I'm going to show you now is that essentially we'll be pushing this equation 1 order further next. So we'll see third derivatives here, third derivatives here. But then that's not something you have in this simplified model. Okay, so here you see that just basically because this expansion is stopped at order 2, that's only usable in linear bifurcation analysis. And that's not so easy to realize, because what we'll be doing next is pushing the expansion 1 order further, but we are still working in the neighborhood of the bifurcation point. So in some point we are still working in the neighborhood of slab configurations where you expect these type of approximations to be valid. It's just not going far enough. Okay, and that, again, that's a tricky one. Okay, I need to introduce some notations that we have to deal with, so it's not too bad. So remember, we introduced 2 derivatives of the energy. Now I'm going to introduce more derivatives of the energy. So we could iterate, and I'll show you on specific examples. We have the first and second variation. We could have the third J variation. Okay. So the quantities Qi I'm defining here, they are obtained by taking the energy, then the J's variation of the energy, and that has to be a multilinear form with respect to some increments which are called x1, xj. So again, we've seen that for j equal 1 and j equal 2. That's what we should do here. Then the next stage is to replace the argument by some point sitting on the branch. So you'll see that we will take variations, and then at some point we'll substitute any remaining x by x naught. Okay? And that's what I call Qi. Or I mix up these. So it's just a linear form, multilinear form that can be, that's now a function of where I am on the fundamental branch. Remember that this is essentially my arc on the fundamental branch. Okay? And now, because that's a multilinear form that depends on lambda, I can take derivatives, right? So the j's derivative would be prime, second, up to the j's derivative. Okay, so it looks a little bit strange, but you'll see on examples. So take the Rayleigh Taylor instability, for instance. Remember, the energy is like that. The first variation of the energy looks like that. I need to, let's assume I want to calculate Q1 prime. So Q1 is really what I had already before, by substituting in the first variation the homogeneous branch. That's the not notation here. So the prime would be just the derivative of this for fixed increments, so for a given x hat, and there's only one increment. For a given x hat, I'm just taking the derivative with respect to lambda. So I have a complicated derivative here, I have one easy derivative here, and I just need to do that in sequence. But at the end of the day, that's another linear form. Okay. So there are two things we should note. First, as I said, Q1 is already the one that corresponds to the nonlinear equilibrium, and it's expressed in the fundamental configuration. So by definition, this is 0, just because my fundamental branch has to satisfy the nonlinear equilibrium. That's why I've been assuming since the beginning. Okay? So this Q1 is actually 0 on any virtual increment. Is that okay? Also note that Q2, it's the second variation. It's really the one that I was using to write the linear bifurcation problem. So the linear bifurcation problem writes this way, and it's going to be 0 if I substitute lambda c and the true mode here and any virtual displacement. Okay, so Q1 and Q2 are known things. Now, because Q1 is 0 for any lambda, in other words, the equilibrium is satisfied on any point of the fundamental branch, then the derivative of this with respect to lambda has to be 0. So all the derivatives of Q1 will also be 0. Okay? So let's look at an example. Actually, no, the example comes later. Now comes the nasty, a little bit nasty part. But so the idea of the Lyapunov-Schmidt-Poynter expansion is that so we are near a point here, which we know is critical. So the idea is let's just try to find a parametrization of another branch that's hopefully sitting there. And let's call them eta. Eta will be an arc length parameter along this branch, right? And we focus on a neighborhood here, so we can take eta as a small point. So the idea is to find lambda as a function of eta and x as a function of eta. This way. So there are two small remarks. First, you could think that it's a good one. I think pretty much anyone would actually try to seek x as a function of lambda. So it's possible, but that's really inconvenient, and actually it often doesn't work. If you have a bifurcation like that, symmetric one is probably the most common type of bifurcations, then x is not a regular function of lambda. You introduce singularities, or lambda is only on one side, so that's a bad idea. So that's all this idea of introducing the arc length. And now the arc length is a convention, so it's possible to change to reparameterize and change the eta, but essentially we eliminate eta at the very end, just for the sake of deriving the equation. So that's the first remark. The second remark here is that note that we are expanding like that. So for any value of lambda, this would be x naught sitting on the fundamental branch. And what I'm seeking is the delta x here between the point on the fundamental branch having the same lambda and the point on this branch, right? So this is this thing. You could instead try to put x naught of lambda c and the expansion, so that looks like a small change, but it simplifies the calculations a lot. So that's let's say that's a trick. Anyway, you come up with expansions for lambda and x, the parameterization of the bifurcated branch by this parameter eta. And now it's just an expansion problem. It's just calculating Taylor series. You want to satisfy the nonlinear equilibrium, which is the first variation of the energy, on this branch, right, for arbitrary increments. So it's just a nasty Taylor expansion problem. You have to insert that, and CD lambda is also given by this. So it's a lot of composed function, but you can do this typically using a symbolic algebra or by hand if you're really up to. You expand this thing order by order. So let's see, at order 1, so if I take eta equals 0, you find that the gradient is evaluated at lambda c and x naught of lambda c. Okay, but that you know already. That's the equation of equilibrium at the bifurcation point, which is just one point among others on the fundamental branch. So that's already known. So you don't learn anything. The equation is automatically satisfied at order eta. And now you can continue. And the nice thing is that at every order, the expressions are relatively simple in terms of the parameter q. So let's look at the first order. So the first order, let's see, comes from actually this term here. So there's a first variation here, then you linearize with this parameter. So you need the second variation in the direction x1, and that's what you have. Okay, there's this increment here, which you have already. There are other terms that cancel out, and I'm not going to. It's quite easy to see, but at first order, that's all we have. So these equations should be satisfied, and every Q1, Q2, Q3 should be satisfied for arbitrary values of the increments here. And the problem now is to find x1, x2, x3, lambda 1, etc., lambda 2, so that this is satisfied. And in principle, if you can do that, this is going to solve your problem because you'll find the predictions that you need here, and you have some description of the branch. Okay? So how does that work? Well, and the point is that, okay, that looks a little bit nasty, but first, this calculation is done once and for all. You can always reuse this, or it's found in many papers. You don't need to do it. That's the first thing. And the second thing is that many of the terms would actually, you don't need many of the terms. And what you need to solve is actually simple. Okay? So take it for, we take this as a starting point that we want to solve these things order by order. Okay, so let's look at, let's try now to see how the solution goes. We take the first term, which is Q1. Okay, so how are we going to solve that? Any idea? So I want to find x1. It's a variational problem. So that has to cancel for arbitrary x hat, right? So you can remove x1, x hat if you want. That's an equation for x1. How am I going to solve it? No idea? Let me give you a clue. We've seen that before. Remember what Q2 is? So Q2 means that's the second gradient of the energy. Okay, so what's this? Oops. What do I get by solving this for x1? Yeah, that's the linear stability we've solved the problem. And that's why you solve the linear stability problem, because that's the first ordering the thing that gives you the branch. That's why the branch is sitting there. Okay. So good news, nothing to do. we just need to use the x1 which we know from the linear stability. Okay, now
the branch could also be negative.
Sorry?
It could also be a negative eigenvalue here.
What do you mean negative?
Q2 could have negative eigenvalue from that. Could go along an unstable branch.
Yeah, definitely. Well, like in the Elastica, where you can apply this method for the third bifurcation of the Elastica, and you would be able to multiply this, and then Q2 would be
Also for the subcritical branch.
correct. Yeah, that works for any branch. It's completely. So we have to build the branch first, and then discuss stability later. Right? Yeah. So for the moment, we forget about stability. Okay. So I think I'll stop here. Well, in just 5 minutes, and just explain to you how things are going for the rest. So now we actually know that we need to take the x1 that has been determined by the linear stability column, and now we need to solve this equation. Okay? And again, all these operators are a little bit painful, but they can be calculated. And it's just a multilinear, well, think of them as tensors. So that's a matrix, that's a third of the tensor, that's a matrix. We know them. We know x1, and now we want to solve for x2 here and lambda 1 here. So how does that go? Well, so we want to solve this equation. So the first thing is that, okay, we want to solve for x2, but what comes in front of x2 is where the place where x2 enters is this q2c, which you can think of as a matrix. Okay, so is the matrix Q2C invertible? I mean, in principle, you can think of this as a matrix multiplication on both sides, right? So that's something we can, well, let's not talk about this one, but for instance, that's something we can calculate. So essentially, we need the inverse of Q2C. Okay, and that's really the reason why I'm using these weak formulations, because what I'm going to say is it's visible here, but it's not otherwise. Well, QTC is not invertible. What do we know about QTC? This. We know that x1 is sitting in the kernel of Q2C. And that's what makes this expansion interesting, is that it's an expansion that uses a singular matrix all over the place. Okay, so that might not be invertible. So what do we need to do? Because we're about to solve a linear problem that involves a singular matrix, we need what's called a Fredholm alternative or solvability condition. We need to make sure that whatever is here is going to lie in the image of Q2C. And that's very easy. We just substitute x hat by x1. What happens then? We might. I mean, this equation has to be satisfied for any x hat, right? So the point of doing that is that if you put x1 here, because x1 is in the kernel of Q2 in this matrix, Q2 is symmetric, then that terms cancel. And you have a condition on this for this problem to be solvable for x2. So that's why it's called a solvability condition. So we should go ahead, and also the solvability condition is this. We just insert x1, we get rid of this term, and we have an equation here. Okay, so that's x1, 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 so that we write this x1 cubed, x1, x1, and we have these two terms, so now we have a linear equation for lambda 1. Okay, and remember, that's known. It can be calculated. I'll show you examples. X1 is known from the linear stability analysis. That's known, and that's known. So we just have to calculate these numbers in curly brackets. When we calculate these numbers, we get lambda 1. And we have the start of the branch. So lambda 1 is actually the tangent here. Okay, I'll show you examples. And in principle, you can continue this, and then you can calculate x2 and the other lambdas. So that works well, and I'll show you examples. Oop, and I'm almost at time. So that's usually what we should do. There's only one problem. When this cancels, you find lambda 1 equals 0. So that's not very useful as a tension. Well, I mean, it tells you that there's a vertical tension. And that's usually the sign that we are doing a symmetric bifurcation, and that the bifurcated bunch is like a parabola. In that case, we are interested in calculating the next term in the expansion, which is lambda 2. So I'll show you next week how we can do that. But that's really the first result we have from this Taylor expansion, and it's really a recipe. You want to calculate lambda 1, you just calculate these two numbers by finding out what the these Q forms are, and you just condense them with the known mode. Okay.
Is it correct that the lambda 1, the third term is the Q2C or Q2C prime?
Sorry, the third term?
Yeah, the Q2C.
That should be trivially 0.
No, it's the one that comes from here. So it's free.
So the third term.
Multiplying lambda 1.
What do you call it?
The third term.
Oh, there's a.
Or Q2C prime. The typo.
Oh, I don't think so, but.
If you plug in x hat to be x1, that term is vanished to be 0.
X. No, so this one cancels.
But the same thing. Plug in this one.
Oh, you're right. Yeah, that should be a prime. You're right. Thank you. Yeah, that's a prime, I guess. Yeah, it's very likely a prime. I checked, but it's prime. Yeah, thank you. Okay, so let's stop here. We have just started to see how it could work, and we'll do the application next week. Okay. Okay.
I found Euler questions for my solution. I worked in objectivity of my function. And it's in a pretty nice form. I'm at the point where I'm going to start plugging in my actual inertial tensors.
Okay, good.
So I got
Good. Well, combining the two might make things
Yeah.
go up, but it's nice at least if you have
There's a
nice separate things.
Yeah, there's a nice form where I don't actually take derivative of my director fields anymore. Only with respect to the angular velocity and the time derivative of the sine y. So that's simple enough for me to move on.
Okay.
I'm sorry, I didn't.
So I think you click